So firstly, I'm going to set some background information in order to set the context in which this work has been done. So bet365, we were founded in the year 2000. We're located in Stoke-on-Trent. We're the largest online sports betting company, and we have over 19 million customers. We're one of the largest private companies in the UK, and we employ more than 2,000 people. In the tax year 2013 to 2014, over £26 billion was staked. And last year is likely to be around 25% up. So we're a business that's growing still very rapidly. We're a very technology-focused company. And these big stats show that this is the case. So I won't go over every single stat, but you can see, for example, our push systems, they burst to 100,000 changes per second, and we have over 2.5 million concurrent users of our push systems. So we have two main production systems that are using Erlang and Riak. They are cash out, and that's a system used by customers to close out bets early, and a project we call Stronger. And this is an online transaction processing data layer. This talk is mainly based on the experiences with Stronger. So why Erlang and Riak? Why did bet365 choose Erlang and Riak? So our historical technical stack is very pragmatic. It's what would deliver a quality product to market in record time. It's mostly .NET with some Java middleware, and it's lots and lots of SQL Server. But we needed to change the complexity of the code and the systems, and we needed to make better use of multi-core CPUs. We needed to scale out. We can no longer scale our SQL infrastructure. This is scaled out, up and out as far as we could, and this lack of scalability caused undue stress on the infrastructure. This led to a loss of availability. So our Erlang adoption. I won't go into the ins and outs what Erlang is or what it does, because I think you all know that already. But some key learnings from our use of Erlang. So you can get a lot done in a short space of time. So we found this to be a plus and a minus. So the time it takes from a developer to hate Erlang at first to love it is really, really quick. And we found that to be quite surprising. I think it's because Erlang makes concurrency a lot easier. And therefore, I feel developers feel like they can build everything. And then you've just got to make sure that they don't. Tooling is limited. So a lot of our developers are used to Visual Studio. Compared to that, Erlang does have limited tooling, or at least less polished. However, I feel like getting developers to do more for themselves at lower stack is beneficial. Hot code upgrades with state can be hard. Dependency management could be better. I hear that Rebar 3 could help with this. I feel it's important to get as much visibility into the system as possible and as early as possible, and to understand how Erlang works with this data. So for example, just because you may be seeing CPU usage, that doesn't directly correlate to actual work being done. Use OTP and reuse proven code. So Erlang and OTP have a lot of useful libraries and APIs. Get to know them. Try not to reinvent the wheel. It also leads to good, clean code, I'd argue. And also keep to standards. So for example, code layout seems trivial, but I think it helps new Erlang developers get on board with a project when referring to Erlang documentation, and it helps integrate with tools as well. Check your supervision tree. So it's something that you normally create when you first start a project. You've got to make sure you keep an eye on it and it stays relevant as the project grows. I said that message passing is a double-edged sword. So what I mean by that is Erlang, I think, makes concurrency a lot easier. And I do like the actor model and the message passing. But you've just got to be careful how many messages you have in your system. It can become a performance bottleneck. So you've just got to be aware of that. Keep state small. So for example, gen server state, it is useful to have state. You just got to be aware how much state you have and try to keep it to a minimum. Also, if a state needs to be highly available and persistent, I'd argue that you should be looking at things like Riak, for example. Binaries and garbage collection. So we do like binaries, and we find them to be incredibly useful, more useful than list-based strings, for example. We've just got to be aware that binaries up to 56 bytes are stored on a process heap. Otherwise, binaries are stored on a global heap. So you've got to be aware of when they get garbage collected. So binaries only on the global heap only get garbage collected when all the referencing processes no longer reference them. So you just need to be aware of your binaries, how big they are, and how it will affect your garbage collection in terms of the processes that use them. Explore whether you need to use the transparent huge pages feature in the Linux kernel. So we found for some of our use cases that use a lot of memory, it was best to disable this feature. Don't use error logger as your main logger. So we found it was best to use a login dependency such as logger login. And validate all data coming into your Erlang system at the edge. General good practice from a security perspective, but I think it also helps with Erlang. So when you track those data type problems further on up the stack, I think it's easier to debug and you get better error messages out of Erlang. So our Riak adoption. Some of you may not be aware of what Riak is. So a very brief summary. So Riak is a key value store. It's soon to be known as Riak KV, if not already. It's inspired by the Dynamo paper. So that's the Amazon paper. It's traditionally a eventually consistent system. So that's an AP from a cat theorem. And then within bet365, we do use it in an eventually consistent way. In Riak 2, they introduced the option of having a strongly consistent option as well. So that's a CP from the cat theorem. With Riak, a Riak cluster is a 160-bit integer space. That's known as being the Riak ring. It's split into partitions. A virtual node, what's known to be a V node, is responsible for each one. A V node then lives on one of the Riak nodes. And then data is then stored in a number of partitions. And this is controlled by the nval setting. And this has a default of 3. The consistent hashing technique then helps identify those partitions for putting, that's writing the data, and getting, that's reading the data. And Riak will do its best effort to make sure the data is stored on different physical nodes. So why Riak? Why did bet365 choose Riak? So there's an open source aspect to it. It uses Erlang. It's based on solid ideas with the Amazon Dynamo paper. It's horizontally scalable. It's highly available. And there's no global locks. So performance is more predictable. It's designed to be operational simple. So that's taking nodes in and out of service, for example. And there's support and community exists for it. So our key learnings from using Riak. As I mentioned, we use it in an eventually consistent way. So this means eventually the data will converge to a consistent value. So practical things to keep in mind. A get, like I mentioned, that's a read, may return an old value. A put, so that's a write, may be accepted for a key at the same time as another concurrent put for the same key in a cluster, because there's no global lock-in. So you might need to bend your problem. So what I mean by that is, for example, if you've got a counter and you're waiting for it to reach a certain value before you do only one action in a highly available way, you need to consider what happens if that action happens more than once. Can you read the side effects in such a way where you only see the side effects once? Data model for your use case. So normalization isn't key. You'll need to trade off your puts against your gets for your use case. So for some of your use cases, it might be better for you to store that data more than once. So when you come to read the data for a particular use case, you can get all the data you need for that use case in one get or as minimal gets as possible. But obviously that's going to impact your puts. So it is a trade-off between your puts and gets, and it will depend on the use case. We found it's best to have no bigger object sizes, 1 megabyte. Again, that's going to be a trade-off between your puts and gets, because you don't want your object sizes to be so small, but you do have to do loads of gets in order to get your data for your use case. So again, it is a trade-off. Store your data in a structure which helps with version upgrades. So if you want to change the structure which the data stored within in Riak, what's going to happen to the data that's already in Riak and already in production? How are you going to upgrade that data? So pre-think that out before you go live. Riak Enterprise exists, so something to bear in mind. Multi-data center replication exists and support as part of Riak Enterprise. Consult Riak system performance tuning documentation. So Basho have some good documentation, but I'd point this one out explicitly. Riak is quite chatty internode, so consider having a different internode network versus your inbound. Riak is network and I/O bound, so make sure you monitor your network and disk usage. Use the Riak admin diag command. So this will do some common checks for you, some common checks in order to check common problems with a Riak cluster. Basho have something called Basho Bench. So this is an independent test tool you can use to load test your Riak cluster to make sure it's as you would expect before you start adding variables in, like your own application on top of Riak. For the Bitcast backend, load test merging and tune for your use case. And you can use a setting called log needs merge. If you set this to true, it will explain in the logs why it's doing merging. And based on this, you'll be able to tune for your use case. Allow siblings, so that's allow multi to be true. And try to resolve siblings as soon as possible so you don't get sibling explosion. Now this leads me on to what are siblings? So a sibling happens when Riak does not know which value is a causally recent. So for example, this can happen because of concurrent puts. It uses version vectors to know this. So version vector A is concurrent to version vector B, as opposed to descends or dominates. I'll explain later what a version vector is. It is referenced as being vector clocks in the Riak documentation. I have seen some videos and literature where it says it should have been named as version vectors. Similar logic between the two, subtle difference. Vector clocks is about tracking events to a computation. Version vectors is about tracking updates to data replicas. In Riak 2, they introduced the option of having dotted version vectors instead. So this is a similar idea to the ORSWOT CRDT dot functionality, and I'll explain that later on too. It reduces the potential number of siblings, so it does causality tracking a lot more accurate, and because of this, it limits sibling explosion. So if you are using Riak 2, I would consider using dotted version vectors. When you have siblings, all sibling values are returned. So that's more than one value. Obviously, that's a massive difference compared to your normal experience with SQL-type data stores. You can set allow mult to be false. So you can set it so no siblings get returned to a client. And you can set this with last white wins to be false. This will use version vectors. And in a conflict, the sibling with the highest timestamp will win. And then you can use it with last white wins set to be true too. So this is a subtle difference. It doesn't use version vectors, and a new value overwrites the current value. Not using siblings isn't recommended because of potential data loss. So network problems, complexity of time synchronization across servers. You perhaps might use it if you had truly immutable data with separate unique keys. However, as a general rule, you should be using siblings. So how do you deal with these siblings? So as I mentioned, sibling values are returned on a GET request. So you need to have a merge function which will take these sibling values in and produce the correct value. It's been shown that this merge function needs to be deterministic by having the following properties. That's associativity, commutativity, and idempotence. It can be hard to get this merge function correct, and if you don't get it correct, it can lead to potential data loss and incorrect data. So this leads me on to CRDTs. So what is a CRDT? So generally speaking, they stand for conflict-free replicated data types. And they can be operation-based, and that's commutative replicated data types, or they can be state-based, and that stands for convergent replicated data types. They reduce the complexity by having no client-side siblings, but you still don't have that data loss, so it deals that merge type logic on your behalf. You can see on the presentation slide, there's a number of readings that I would recommend which explain where CRDTs came from. So operation-based CRDTs. As I mentioned, they're called commutative replicated data types. With operation-based, all replicas of a data are sent operational updates. It relies on a good network and reliably delivering these updates. Also, knowing the current true membership is more important. With state-based, as I mentioned, they're called convergent replicated data types. The data is locally updated, sent to replicas, and merged. This update function must be monotonically increasing. It is generally easier to understand than operation-based, and it is easier to have an elastic membership of replicas. However, because you're sending around the state, and not just the updates, more data is sent around the network. So you can have different data type implementations for CRDTs, such as counters, sets, maps. For our core use case, the sets data type made sense. However, we were, and we still are currently, using Riak 1.4, and a set CRDT wasn't available. This was something that was introduced in Riak 2.0, and at the time when we were doing this project, Riak 2 wasn't even a release candidate. So what did we do? We decided to use the Riak DT dependency that has a CRDT functionality within it and integrate it ourselves into our system using Riak 1.4. An advantage of open source. Different set-based implementations exist. So there's a G-set. So this is a Grony set. You can add elements, but you can't remove. There's the OR set, and this is the observe remove set. You're able to add and remove. However, when the element is removed, you still get a tombstone. So a size problem exists. If you had a set of like 100, for example, and took some elements out, the client would see those elements as being removed, but the size of the set would still be the same. And then there's the ORSWOT. So the ORSWOT is the observe remove set without tombstones. So you're able to add and remove, but you don't have the tombstones. So you don't have a size problem. In a concurrent add and remove of the same element, the add wins. You can have implementations where remove wins, but generally the add wins. And you can see a reference on the presentation slide which explain where ORSWOTs came from. For our core use case, we chose to use the ORSWOT. So what is the ORSWOT? You can see an example on the presentation slide. So you have your Riak key, for example, and you have your value. And the value is the ORSWOT. in your ORSWOT, you have a version vector. So you can see this in green. And this exists as part of the ORSWOT. It's a list of tuples, each tuple being a unique actor name and counter. All ORSWOT operations then happen through a unique actor. It's similar, but it's a different instance of version vector to what would also exist for the overall key value. You then have your ORSWOT entries. Each ORSWOT entry then has your element, your data, and it also has what's called dots. So you can see this on a presentation slide in blue. So dots exist for each element of your ORSWOT set. It's just a minimal version vector, and each dot pair represents a tuple in the ORSWOT version vector at a particular point. It's usually listed as one, but it can be more, and I have an example later on where you see where the dots are greater than a size of 1. If you were to add an element to an ORSWOT, the version vector as part of the ORSWOT is incremented. So this means the counter for the unique actor being used is incremented, or set as being 1 if that actor doesn't currently exist in a version vector. This updated unique actor name counter is then stored with the element as its dots. So best with an example, quite straightforward, but you can see one on the slide, where if we add data 2 using unique actor y to the existing ORSWOT, it results in a new ORSWOT where a version vector has been incremented, so you can see y1 has been introduced. And this y1 is then stored with the element as its dots. In this example, you can see data 2 being stored with y12. To the client, they'd be interested in the core data. So in this example, it would be just data 1, data 2. The rest of this data as part of the ORSWOT is its metadata. So how would you remove an element? So a version vector as part of the ORSWOT does not change, so the green bit. But of course, when you change the ORSWOT value and you put it back into Riak, the version vector as part of the overall key value would change. The element's entry is then simply removed from the ORSWOT. Again, a basic example on the presentation slide. If we remove data 1 from the existing ORSWOT, it results in a new ORSWOT where the version vector in green does not change, and we simply drop the ORSWOT entry for the element data 1. So you can see the element and its dots are simply removed from the ORSWOT. There is your further option to be able to do delayed or deferred removes. So you'd want to do that when the ORSWOT object during the remove has not seen the original add for the element, e.g. because of being a replica which hasn't seen the original add. That's an implementation option that you can have. And it would add further logic to remove, and it would add further logic to the next slide, which is about merging. So how would you merge two ORSWOTs? I do have an example on this on the next couple of slides, which I think shows this better than listing out all the kind of instructions. But I will briefly go through it. So you would merge ORSWOTs when you have, for example, siblings which have been detected by the overall key value version vectors because you've had concurrent operations on your ORSWOT. So if you were to merge ORSWOT A and ORSWOT B, to get the merge version vector, you would take the least possible common descendant of ORSWOT A and ORSWOT B. Like I said, I do have an example. The elements are then merged. So first of all, you look at the common elements. And the common elements are only kept if there exists a non-empty dots for them after merging the following. So the common dot pairs for the common elements in ORSWOT A and ORSWOT B. Dot pairs for the element only in ORSWOT A, where a dot pair count is greater than any count for the same actor and ORSWOT B's version vector. So you're comparing the dot pairs in one ORSWOT to the version vector of the other ORSWOT. Then you do a similar thing to the dot pairs for the element only in ORSWOT B, where a dot pair count is greater than any count for the same actor and ORSWOT A's version vector. You then look at the elements only in ORSWOT A, and similarly, they're only kept if there exists a non-empty dot for them after keeping only dot pairs for the element where a dot pair count is greater than any count for the same actor in ORSWOT B's version vector. And then you do a similar thing for elements only in ORSWOT B. And like I said, I think it is best explained with an example. So if we had ORSWOT A, and this is seen adding element data 1 by actor X, adding element data 2 by actor Y, and then adding element data 3 by actor Y again. We then have ORSWOT B, and this is similarly seen adding element data 1 by actor X, adding element data 2 by actor Y, and it's also seen adding element data 3, but this time by actor Z. So it's been a concurrent add of the same data, which is data 3. It's also seen adding data 4 by actor Z again, and then removing element data 1 also by actor Z. So this results in the merged ORSWOT as seen on the presentation slide. So you can see that data 1 has been dropped. You can see that data 2 and data 3 has been kept. And you can see that data 4 has also been kept, even though it only exists in ORSWOT B. So if we were to explain that better and to break it down, so in a merged ORSWOT, X1, Y2, Z2 is the least possible common descendant for the version vectors ORSWOT A and ORSWOT B. So you can see this because you've got X1, which is the same in A and B. You've got Y2 because that's greater, the greater Y, which exists in ORSWOT A. And you can see you've got Z2 because it only appears in ORSWOT B. We then look at the common elements. So first of all, we've got data 2. Data 2 exists in ORSWOT A and ORSWOT B. And they both have a common dot pair, Y1. There are no other dot pairs to consider as part of ORSWOT A and ORSWOT B for data 2. So we just have Y1. That's obviously a size greater than 0. So the element is in. We then look at data 3. So for data 3, ORSWOT A has Y2. And this is greater than the count Y1 in ORSWOT B's version vector. So obviously Y2 is greater than Y1. So that's considered. We then look at ORSWOT B. So that has Z1. And this is included because ORSWOT A's version vector doesn't have a Z, so it's greater than ORSWOT A's version vector. This results in Y2 and Z1. This is merged to obviously give a list greater than 1. It's greater than 0, which is 2. And therefore the element's in. If we then look at elements only in ORSWOT A, so this is data 1. So from ORSWOT A, there's no dots exists from X1, which are greater than ORSWOT B's version vector. So obviously X1 isn't greater than X1, which is in ORSWOT B's version vector. So the element is not in a merged ORSWOT. We then look at elements only in ORSWOT B. So this is data 4. So we can see that from ORSWOT B, dot pair Z2 for the element is kept because ORSWOT A's version vector doesn't have a Z. So therefore, data 4 is included in merge ORSWOT. So our Riak DT integration. For this, we needed to have an Erlang middle layer between our client and Riak. This middle layer needed to have unique actors. We use gen servers as part of using this ORSWOT implementation. Now we need to get a balance on a number of them due to impacting the ORSWOT version vector size, but also obviously too little and it would impact the concurrency of a system. Each unique actor needed to have a unique actor name. And this was predefined as part of the server setup configuration. And we needed to make these unique actor names as small as possible due to also impacting the ORSWOT version vector size. So this meant our clients didn't have to deal with siblings. However, this middle layer, i.e. the client to Riak still needed to bring back these siblings and do this CRDT merge logic. So it's still not as good as having Riak's server-side CRDT, as in Riak 2, but as I mentioned at the time, that wasn't available. And as I suggested on the previous slides, we're still using version vectors on the overall key values to know, for example, to do the ORSWOT merge operation, because there's been concurrent operations on the ORSWOT. So how do we get a system live like this, considering it's a mission-critical system, and bearing in mind it's replacing a current system which is always moving? So first of all, tooling. So from day one, we had our own dog food. So what I mean by that is that we invested in tooling at the start of the project, and we used it throughout the project lifecycle to make sure it's fit for purpose. So we invested in monitoring, we invested in performance counters. So this Erlang middle layer, for example, had stats and counters functionality, which allowed us to have basic counters and latencies at a global level for requests. But it also, for a particular request, if it was deemed to be higher than the acceptable latency, it would print out a timeline. And this allowed us to debug problems. And this proved to be really invaluable. There's error reporting, including thinking about correlation between systems and how you track an error through a system or its progress. We built a custom ad hoc query tool. So this went through our Erlang middle layer. And this was able to take advantage of, for example, the CRDT functionality. And for good practice, we also run this on the replicated Riak cluster. We built custom reconciliation between our new system and old system. So given the same input, do they eventually have the same output? Do they have the same data? And we also created build and release scripts for automation. We released the project in phases. So this allowed us to build on stable ground. It allowed us to get data to impact future decisions. And it allowed us to build confidence. We were able to move functionality using Erlang and Riak in a phased way. Not all phases were immediately business impacting, but overall we feel we're able to get business impacting functionality out sooner. Replay testing. So we did replay testing, and we did this by capturing logs asynchronously in one phase. We had a common interface between our old and new systems. And as I previously mentioned, we were able to do reconciliation between the two systems. This replay testing gave us a big range of test data, and it gave us a realistic load profile. It was used for functionality and performance testing, and we had different logs for a long weekend run. That would give us advantage of having more test data, versus a quick run, which obviously had less data, but we had a quicker feedback. This replay testing complemented other testing, such as specific unit integration testing, fuzz testing, and formal UAT. Performance testing, obviously very important. We did it early and we repeated. So we didn't leave it till the end of a project. We built a custom client using these replay logs, and we were able to increase load profile easily. Again, we use our custom tooling and monitoring to make sure it's fit for purpose. So if any problems came up during performance testing, did our tooling and monitoring what we'd have in production allow us to find out what the issue was? If it wasn't, and it's not fit for purpose. But it did. It helped us to get to the problem. With performance testing, we identified bottlenecks, and we tested the horizontal scalability of a system. We also did ad hoc changes because I feel it's important to keep the momentum up during performance testing. And we fed this back into development. Between these ad hoc changes, we had a specific profile which would give us a fair test between changes. And again, as previously indicated, we use Basho Bench in order to sanity test our Riak cluster before we introduced our Erlang middle layer as an extra variable. Failure testing. So we did failure testing, also very important. This built confidence and also our understanding of Riak and our system. We were trying to make sure a failure seen in production isn't the first time it's experienced. We also tested common procedures, including that load, and that's including taking nodes in and out of service. And my message would be that failures will happen, so embrace them, don't run away from them, and make sure your system deals with them, and also test for them. So today we're stronger. So the project was a success. We now have a system in production which is performant and able to deal with many times our peak load. It's reliable, and it deals with failure using minimum human intervention. So for example, we had an air conditioning problem in one of our data centers, and it took some of our servers offline. But to a customer, Stronger had no customer impact. We've also introduced the business to a number of new technologies, and we've grown the capabilities of our business and our people. So that's the end of my talk, and this now leads me on to any questions. Okay, there's one question here. I'm not sure whether mic works, so I'll say it and I'll repeat it. Yeah, sure. Of course, so the question was, what do we do when our ORSWOT values were greater than one megabyte? So there's techniques such as sharding. So we use sharding and compression. So you can use compression too. Any more questions? One more question? I see, yeah. So the question was, which part of our system does this stronger project relate to? Well, it is a cross-functional team project, so it is like a middle layer. Traditionally, we are a betting company, and it started off with the bet placement side of things. Any more questions? I don't think so, so I think we'll call it a day. Thank you very much.